again, in previous lecture, we had a very heavy focus on wearable artificial kidney, and we actually marked the difference between those two approaches. And in this lecture, we will make a quick overview of the concept of the implantable artificial kidney. Specifically, we will talk about cell-based approach and total artificial kidney approach. So just to repeat the main thought, implantable artificial kidney in its core principle has to imitate the work of the native nephron. And basically, if we talk about the two main stages of the blood purification in the native nephron, we have to take into consideration how exactly we perform the blood filtration, like it goes in a Bowman spacer or a glomerular capsule, and how we implement or speed up the reabsorption of water and essential nutrients that are required for the functioning of the human organism. Here's a quick historical overview of the development of different approaches of renal replacement therapy, mainly the apparatuses called artificial kidney. So it all starts in 1945 when the first apparatus of hemodialysis was introduced by Koch. And what this particular plot illustrates is that the idea behind the development of specific renal replacement therapy apparatus, it actually predates the development of the actual technologies that will help to develop the specific apparatus. Because even we talk about the very first artificial kidney, it should be emphasized that the first dialyzer, the first approach of the dialysis was introduced by Thomas Graham in somewhere in 1860s. So it's from our standpoint, it's about 2 centuries ago, or 1.5 centuries ago. And the idea that was proposed by Thomas Graham that we can actually use that method as the device or a method to help the people with some kidney conditions, that was introduced somewhere in 19th century as well. But due to lack of any technology like the anti-thrombosis methods, the specific dialysers that actually provide an adequate transmembrane pressure to perform the autofiltration, it was not possible to develop instantly the apparatus that would help to perform renal replacement therapy. So the appearance of specific apparatuses happens only when a critical mass of technology is reached, when there are different technical approaches and technical possibilities that actually allow us to make it happen. And the same goes for basically any idea we have to. That means that if we have the idea of wearable artificial kidney, we have to develop specific dialysis regeneration approaches that will help us to simplify the development of this particular apparatuses. If we have the idea of implantable artificial kidneys, we have to take into consideration that the conventional methods that are used in the hemodialysis are not suitable for development of implantable kidneys. And what has to be taken into consideration, we have to develop specifically new materials that will prevent thrombosis inside of these apparatuses, that will make possible to perform the blood filtration and the reabsorption methods inside of the implantable kidney device. So basically what this plot illustrates is that there is always a need to develop specifically new technologies that will help us to implement the new basic approaches for new methods of renal replacement. And if we talk about the general approach to how people were trying to find the solution for major problem that we call kidney failure. Let's simplify that we have basically 2 main approaches. The non-cellular approach and the cellular approach. Here we already discussed the hemodialysis apparatus and its modalities. Peritoneal dialysis and its modalities. And here we have the kidney transplantation. Which basically opened the opportunity for regenerative technologies such as tissue regeneration, because the more people research the function and cell cultures of kidneys, that presented the opportunities to introduce the tissue regenerating technologies for kidney. In that regard, we already discussed that both of these methods can be used for development of wearable artificial kidney. The further development of microfluidic system provides us to introduce the microscale dialyzer and hemofilters. The introduction of microfluidic system actually gives us an opportunity to create the implantable kidney. Technology. The introduction of the tissue regenerative approaches and different biotechnologies provides us with the opportunity to create the renal assistant devices that basically, in combination with implantable kidney, provide us with a biotechnology calling the implantable renal assistant devices. And basically, we can divide the whole idea behind the implantable kidney, that we can implement the implantable kidney in non-cellular manner when we do not use any biotechnology, or we can actually combine the biotechnology with the implantable kidney and basically making a renal assistant device that has the biotechnology behind it. So just continuing the main idea behind the implantable kidney, let's summarize the main idea of what exactly we have to imitate inside of this system. So basically, if we remember the first lecture, we are talking basically about the nephron as the structural unit of the kidney. And in case of the nephron, we can simplify the work of this nephron in a very primitive manner, that we have the blood filtration approach, that consequently we have the reabsorption of water and nutrients, then we have the secretion and the removal of the fluid from the organism. So basically, if we're talking about the filtration and reabsorption, we focus our attention to the Bowman capsule, to the glomerular, and to the proximal renal tubule unit that includes the Henle loop that provides the reabsorption of water and the nutrients. So the first stage of the blood filtration takes place in the glomerular unit, where through the transmembrane pressure that is created by the difference of the hydrostatic pressure of blood and Bowman-based liquid, we create the initial ultrafiltration that leads to the formation of the primal urine. It goes to the proximal convoluted tubule. It goes to the Henle loop, where we observe the reabsorption of the nutrients and water, and then the final product goes to through the secretion and removed through the bladder. That's basically the breakup of the blood filtration in the natural nephron. Here is an explanation behind the pressure, that the arterial creates the blood pressure, and the difference will be about 55 mmHg, and that's the glomerular filtration rate. And there is a difference basically between the blood flow and in the efferent arterial and the efferent arterial that is created by the filtration rate. And if we talk about the historical perspective behind the development of implantable artificial kidney, we can mark up the milestone of creating a renal assistant device that was introduced in 28 by the Dr. David Humes. And basically, the main idea behind this invention is an attempt to imitate the working of the nephron in the matter that we use the hemofilter and advanced the hemodialysis, just like we observe the filtration blood in the nephron. We have the glomerular unit that basically is a natural hemofilter, and we have the proximal convoluted tubule with Henle loop that provides the reabsorption of essential nutrients and water. So basically what motivated this idea is that if we talk about the conventional hemodialysis method, we basically have only one mass exchange unit with semi-permeable membrane. And we have a perfusion circuit where we have the blood flow and the dialysate flow. And we have some different mass exchange processes that take place in this mass exchange unit. So the main issue with that particular method that we do not introduce the essential nutrients that will be filtered in the mass exchange unit. The membrane is usually non-selective. That means that all small-sized molecules will easily penetrate the membrane and they will be filtered out by the dialysate fluid. That means that if we have some small-sized essential nutrients that should be reintroduced in the patient during hemodialysis, we have to reintroduce it artificially by making some infusion after the initial filtration. And basically, there is no way we can imitate the work of the proximal convoluted tubule. There is no reabsorption here. There is basically ultrafiltration and filtration of uremic toxins. So the idea was, if we talk about the way how nephron works, the idea was to implement basically what we observe in a natural nephron. So we could introduce the hemofilter, a unit that has only one exit for the ultrafiltration, by creating the transmembrane pressure in the blood circuit. We acquire the initial ultrafiltrate that goes to a modified mass exchange unit. And this mass exchange unit actually has the culture of cells that are positioned in the blood circuit. And that goes back to patient. Those are usually the tubal epithelial cells that provide the reabsorption of nutrients back to the blood from the initial ultrafiltrate that we removed from the patient. And basically, this hemofilter works as the glomerular capsule, while this modified dialyzer works as the improvised convoluted proximal tubule. And the first implementation, that's actually the renal assistant device. It was implemented in the hemodialysis system as the method to cope with the problem of the nutrient loss during the hemodialysis approach. And basically, if you look through the literature and you look about any information about implantable artificial kidney, first and foremost, what you're going to actually find in this literature is an attempt to implement the approach in the form of renal implantable artificial kidney. So basically, it's an attempt to combine biotechnology and artificial technologies that help us to imitate the work of natural nephron. And that's basically became a new way to develop the new type of bioartificial kidneys. So it did not just stop with the renal assistant device. The next approach was an attempt to create the bioartificial kidney that introduced the type of cells that started to generate a morphogenetic protein that is basically a protein that helps to regenerate some lost functions of the kidney. And the implantable kidneys, usually when we talk about the current stage of the prototypes that include implantable artificial kidneys, it's an attempt to combine biotechnology and the blood filtering technology. Although, as we addressed this in the last lection, there are actually attempts to create a totally implantable kidney that will use the approach that will not introduce the biotechnology at all. Because despite the fact that this method is actually quite prominent and in some cases very effective, because the cell culture in fact helps to reabsorb some essential nutrients during the blood filtration, there are multiple complications and technicalities that make implementation of biotechnology a very challenging issue for implantable kidneys. The next approach actually requires the introduction of the specific biotechnologies that combined in the tissue engineering. So if we talk about bioartificial kidney and the renal assistant device, it all revolves around tissue engineering. So if we remember our previous graph that we were talking about earlier, the implantable kidney that relies on biotechnology heavily relies on the tissue engineering approach. And if we talk about the current most prominent prototypes of implantable artificial kidney, such as the first prototype of X kidney, it's basically an attempt to implement the system that was discussed earlier in a form of a very small apparatus that combines the hemofilter and bioreactor. So what is the problem? Why it was not done earlier? The problem is that we cannot use the conventional membranes that we use in a hemodialysis. We need a specific new technology that helps us to implement like a micro-sized hemofilters and hemodialyzers that will be implemented in a form of a very small hemofilter, and the same goes for bioreactors. So in order to achieve that technology, we have to develop a brand new type of membranes that basically help us to miniaturize this apparatus, and basically it will make it implantable for a human. In case of the huge difference between wearable artificial kidney and implantable artificial kidney is that in that case we actually imitate the work of nephrons. So we basically in hemofilter, we acquire the first ultrafiltrate that we send to bioreactor. or any type of unit that imitates the proximal convoluted tubule. The reabsorption help us to return the nutrients back to blood that goes back to the vein, and then the final urine goes to the bladder. And the main idea behind this apparatus is that we use the cardiovascular system without any additional pumping. So basically, it's an attempt to recreate the artificial kidney the way how the natural kidney works. Here's the small illustration of that kidney project that has been developed in San Francisco, the USA. And here is the depiction of the artificial implantable kidney that exploits the biotechnology. So basically, we need a specific membrane that's basically a silicon nanoporous membrane, as far as, if I recall correctly. And you can notice that on top we have the biological cells, and they are separated by another membrane. So why exactly it's the case? The problem is if we have the direct connection between the biological tissue and the patient's blood, there is also always a chance that there will be an immune reaction to this biological cell that we introduce in this apparatus. And that's the main technical issue that technological implementation actually has with that. And that's what makes development of this apparatus very challenging problem that has to be dealt with. Because even if we take a cell culture from patient himself and we grow these cells that were actually belong to the patient, there is always a very huge chance, about 40%, that there will be immune reaction despite the fact that we took those cells from the patient himself. That's why, in order to prevent the immune reaction, the following problem should be solved by introducing additional membrane that does not allow the immune cells of the blood to interact with biotechnological part of the artificial kidney. And that's the problem that is crucial for bioartificial kidneys. So talking about the new technologies that are required for developing of such kidneys, we cannot use the conventional hemofilters in hemodialysis. That means that we need to find out how to miniaturize these systems and how make it affordable for actual implantation in the human body. And for that reason, the microfluidic system should be developed for this particular reason. So basically, the idea is that we create a sandwich type of the microfluid that has two channels. One channel go for the blood of human blood, and the second channel goes for the ultrafiltration that we acquired during the creation of the transmembrane pressure. And then we use this improvised microchip to acquire the ultrafiltrate and send it to urinary bladder. And basically what makes organ-on-chip such desirable technology is that this type of microchips can be implemented for different types of artificial organs, including the artificial kidney. Because in case of artificial kidney, we can always develop some sort of a hemofilter. So we can imagine that this is not just a regular hemofilter, but rather a microchip where we have the microfluid for blood and we have a microfluid that receives ultrafiltrate. And we basically use this improvised chip to imitate the Bowman capsule. And in that regard, we are not even required on the first stage to use any biotechnology, because we can use just the blood pressure to create the additional, the required transmembrane pressure to acquire the first ultrafiltrate. And what makes these technologies so promising is that we can create a lot of these microchips and we can combine them together and we can acquire a miniature implantable kidney, which will be small enough for implantation in a human patient. So we were talking about the biotechnology a lot, and the biotechnology has actually the problem that if we basically implement the biotechnology, we have to deal with the immune response. And another promising way would be imitation of the proximal convoluted tubule without using any biotechnology. This could be achieved if we actually adjusted the size of microfluids the way that we could use the Bernoulli principle to create the condition when we can actually reintroduce water back to the patient without using the biotechnology. So basically, we could use the geometrical structure of microfluidic system that basically would force by physical means the reintroduction of water from the ultrafiltrate back to the patient. Thus, we could avoid the using of any biotechnology required for that procedure in renal assistant devices. And this approach would be easier in comparison with biotechnologies, but at the same time, biotechnology provides us with the opportunity to reintroduce some cells that could participate with endocrine function, but people always say the big starts with the small, and the small part is, and very essential part is actually to imitate the reabsorption without introducing any additional biotechnology by using just geometry of microfluidic channels. And not just geometry, but the position of different channels that provide the flow of the ultrafiltrate with some substrates back to the blood tubule. And basically, in order to implement this theory on practice, we need to understand basically how the native nephron works in case of simplified mathematical approach. That's what will be concerned in the next tutorial. Yeah. That's just a small table for references. Basically, that's my whole lecture. If you have any questions, I will be glad to answer them. Yep.
In one of the previous slides, you showed arterial pressure, if I remember correctly. It was one of the earliest slides, like really early, maybe the second or third slide. Yes, here. So it's something related to blood pressure or arterial pressure?
Arterial, when artery goes to the kidney, it starts divides on different small vessels, and we actually consider the vessel not of the perhaps of the artery itself, but the arteriole that goes to the glomerule.
So, but is that controlled by the pumping of the heart?
Yeah, it's actually controlled, including the pumping of the heart, because if we actually remember the glomerular filtration rate, let me just introduce this equation really quick. Yeah, if we just try to introduce it, we have the hydraulic permeability, we have the blood pressure minus Bowman liquid pressure, and we have the oncotic pressure created by protein in blood. So we have the main parameter of the blood pressure, and of course we have to consider the pressure that is created by same albumin, and the concentration of albumin can change during the if we consider different diets of the patient. But mostly we talk about the pressure that is created by heart itself, if we can call it that way.
This is just like maybe an out-of-topic question, because yesterday I remember you said that people who develop some sort of chronic kidney disease, they simultaneously or after the development, I'm not sure, also develop cardiovascular disease. Is this what is this connected to the fact that pressure is?
uh, since it's like medicine is not my main field of expertise, I will give like a Dunning-Kruger answer, unfortunately. But yeah, so take it with the grain of salt. I would say that there is some domino effect when, because the all systems in our organism are interconnected. For instance, kidney disease can lead to development of the chronic kidney failure. Chronic kidney failure can lead to the chronic kidney heart disease because there is a malfunction of kidneys and there is malfunction of endocrine function that they support, including the blood pressure. So basically, we can assume that there is such a domino effect when we just remove one essential system, the rest of the organism starts to fail. But yeah, it depends like on the history of the disease development. But we have to take into consideration that everything is connected with everything else. And if we just shut down an essential blood filtration, it will affect the heart function. If the heart function is affected, it can affect the blood filtration. So yeah, it's better to have healthy kidneys.
Thank you.
Yeah, thank you. Yeah.
Hello, sir. If I understand correctly, the main motive behind moving on organ on chip technology is basically to avoid the immune response, immune reaction.
Well, kidney on chip actually gives us opportunity to miniaturize the
Yes,
filtration
yes,
system.
yes.
And speaking of immune response, there we can implement basically implantable kidney technology with both kidney on chip or basically to create implantable kidney, we need kidney on chip technology because it's a small sized filter
Yes.
unit that can be multiplied and put together, and basically we can acquire the implantable system without need to use the conventional materials for hemodialysis because they are very big sized and they are not suitable for implantation and they have different other problems that make it hard for them to be implemented in this technology. But the main reason is the attempt to imitate nephron in a micro level.
Okay. Sir, these bioartificial implantable kidneys, which basically make use of biotechnology.
Yeah.
So, if I compare kidney on chip with this technology, whether since it is miniaturized, the size is getting small. So, whether the efficiency is obtained or not compared to that use of biotechnology.
Um, well, biotechnology actually introduced to imitate the reabsorption function. So in terms of prototypes, like the most prominent prototype right now is the kidney project in San Francisco, and if we are talking about the prototypes that are close to clinical trials, that's pretty much it. And biotechnology is actually a very desirable approach because we can resolve the problem with reabsorption and we can resolve some endocrine functions because otherwise, if we use the totally implantable kidney, there is no way we can reproduce the endocrine function. But reabsorption can be basically implemented by both methods. The only way to test it is to actually whether modeling or testing the real prototypes, and there are like they are not used to publish some very critical data, unfortunately.
Okay, thank you, sir.
Yeah, thank you.
Thank you, sir, for the insightful talk. So, my question is how is the membrane clogging issue addressed in wearable artificial kidney and implantable renal assistant device, sir?
Yeah, that's a very good question and very critical one, because when we talk about the implantable systems, we need to take into consideration that blood clotting will be a very critical problem, especially that goes for artificial heart. And if we talk about the artificial kidneys, it's also a type of apparatus that directly works with the human blood. So basically, the only way, the way that we need to work with that will be concerned on second tutorial, is to develop the specific surface on the internal surface of this microchip that basically prevents the formation of the start of the thrombosis reaction. Basically, a surface that does not allow the initial absorption of albumin starts, because when albumin forms a layer on the surface of the channel, there are next consecutive reactions that actually force the blood clotting. And we whether taking into consideration the blood clotting mechanism, and we prevent the first stage of blood clotting by introducing material. For instance, it could be some organic materials based on carbon nanofibers, or it could be some sort of a heparin surface that basically prevents the formation of the thrombosis. And yeah, that should be emphasized, that we cannot just constantly use heparin here, because it will affect the blood health issue with the patient. So the only way that is possible for such implementation is the development of the materials that prevent the clotting formation, basically on the early stages of the thrombosis. It starts with, as far as I know, with albumin absorption. Yeah.
Thank you, sir.
Yeah. Yeah, that's just a small foreshadowing. Like for a tutorial reason, I asked my colleagues to provide a testing microfluid system that they are working with, and they actually concern the issue with the formation of the thrombosis, and they basically try to develop a film that does not allow during different shear stress of the blood to form the thrombosis inside of this microchannel. So yeah, the main focal point is to develop a new type material that prevents thrombosis. And that's quite crucial for implantable apparatuses, because implantable kidney works with heart, obviously, and implantable artificial kidney obviously has to work with blood. So yeah, I will try to address this issue in the second tutorial. Yeah. Other questions? Yeah, thank you for your attention. I think we can stop or yeah, we don't have curator. Yeah, if you have any questions, feel free to ask. Sorry, contracted a common cold from somewhere.
Okay, this lecture is over now, so we will meet at 3 p.m. again. Thank you for joining.